time. Okay. Hey guys. Okay. Welcome to the stream. Today, it's gonna be a very, very complex, I'd say. You could even say it's integral to mathematics. Yeah, today we're gonna be tackling integrals, okay? You guys will learn math, okay? You have to learn math. You have to learn math, okay? You have to. It's very important. This will, it will cover very, okay, it's mostly just basic stuff in integrals, okay? Integrals, yay, yeah. It'll be, okay, first rules, just basic rules, okay? Antiderivative, the fundamental theorem, and then the just basic u sub, trig sub, by parts, and then the fraction decomp. Yes, fraction decomp. Okay, that's it. Exactly. It'll make you insane. It's making me insane. I am insane. Ooh. Okay. Anyways, how have you guys been? It was the GA earlier. It was very fun. Honestly, there wasn't a lot of people in it. Like, compared to normal GAs in the past, it's definitely a lot less. Nah, this will be more like a review where I'm not gonna test you guys unless you know you want it. You want a pop quiz? Do you want a pop quiz? It's gonna be just mostly reviewing it. Especially for those who have maybe a test, like, I don't know, next week maybe. Test people would test next week probably. This will probably help them. It's just a little reviewer, you know, just like basic questions. I don't think they're gonna be basic. If you don't know it, yeah, you're cooked. If you know it, yeah, nice. But yeah, also going back earlier in the GA, it was very fun. Not a lot of people, but like, you guys should have seen it. There was a whole lot of activities. There were cutouts of us. Very nice cutouts of us. Cheeky cutout was very cute. The cheeky. There's also like a photo wall, big photos during that time. So I don't know if you guys missed it. I don't know. Try again next time maybe. But also there's gonna be an event next week, also Wednesday. Next week Wednesday, there's gonna be like a Pride event. So if you guys are interested in that, maybe you can check it out. But also today, I looked at like the NKK cosplay event. There's just a bunch of cosplays. It's pretty nice. Like Lilia Bear was there. But anyways, it's a time for math. Let's go to the math. It's math time. You know? Okay, wait, where's my drawing tablet? It's not working. Plug it in. Math. Yay! That's Akaru sensei. You know, like math? Well, learn. That's all I'm saying. It's not about liking it. It's about needing it. Well, okay, what other applications of integrals would you need? 1 plus 1? I don't know, 2. No. I think it's 3. Let's wait, what's the 1? Let's say it's a plus a, that equals to 2a, right? Okay, no, I'm not continuing that. 9 plus 10, I think 9 plus 10. Borrowing from this, I think that's 21. That's final answer. Yes, it equals to the square. It equals to a window. That's what 1 + 1 is. It's the window to the soul. So right, yeah. Ooh, we have a math exam tomorrow. Yeah, good luck with that. What even is it about? If it's integrals, perfect stream. If it's not, yeah, good luck. Limits. Oh wait, did we tackle limits? I mean, technically, there is a little bit of limits in integrals. So, yeah, here's literally integrals. Yeah, perfect stream. Okay, let's start with the fully basics first. Integrals. First of all, what are integrals? Number one thing, it's just an antiderivative. That's the basic thing. Antiderivative. Got that wrong. Derivative. It's just the reverse of a derivative at first. Just at first. So let's say, right, d over dx. This requires you to first at least know what the derivatives are, okay? I'm skipping over that. This should have been like last term. I just should have started last term, but the thing is, delays happened, so now integrals. Yay! This is also my reviewer. I also need to review. But yeah, okay. First, d over dx, right? The regular formula for that, the power rule formula for derivatives, it's x, and then to the power of n minus whatever one number, n is the whatever number, but the minus 1, and then you just multiply it by n, right? That's the basic rules. But now, what the antiderivative is, so this little squiggly line that has probably failed a lot of up-and-coming engineers. You know, this little squiggly line has done so much to has ended so many careers. But yeah, this little squiggly line, that equals to the reverse of this. And how do you reverse this? So the reverse of this would just be like, instead of minus 1, it's gonna turn into plus 1, right? And then over here, instead of putting n there, you're gonna divide it by n now. But remember, this is also here. This minus sign is here. So you also apply that here, the bottom. It's gonna become this. X to the power of n plus 1 over n plus 1. That's a basic power rule. Basic power rule for integrals. Basics. It gets harder from here. Sadly, all amount of math gets harder from there. That's just one rule. Most of the time for integrals, it's not even this part. This part is just what you do at the end. Most of the time, it's just trying to, yeah, brick by brick. It's most of the time just trying to permute, or like, is it permute? Permutate equation first. Or you simplify. First. It's mostly that. My handwriting is not great, but it works. So let's say you have this type of equation, something along the lines of 3 over 9x to the 2. Something like that looks so complex, right? You know, like, how am I gonna apply this thing to it? How am I gonna apply that here? Well, actually, it's really simple. It's the weird part. This is one of the rules in integration. you don't have to think about this part of it. You can take that out. And also, you can simplify this. So this, instead of straight up integrating with the constants, you can just first simplify it. So it turns into 1 over 3 x, or like that. But this time, if you're gonna add the if you're gonna integrate it, you add that squiggly line. So it's gonna turn into this, right? 1 over 3 x to the squared. 1 over 3 x squared. But you can also take it out, so you don't have to worry about it, okay? Just take it out of the integral in general, just there. So there, 1 over x squared. That's it. You don't have to think about that constant. You can do it after. See? Because it's basically the same. So you're just gonna multiply it by that. It's got the integration of the actual function part, and then multiply it by this thing. This thing. So how would you do that? Next, you would do this. 1 over 3. Remember, this that's coming from that. But now, actual integration part. So x 2 plus 1 divided I. That's 2, right? 2 to 2 plus 1. It's gonna turn into that. But this time, since you integrated it, plus c. Remember this thing. That's so important. If you don't have plus c, that's like what, 1 minus point, or even 2 or 3. Depends on the prof. But it's gonna miss out on a whole lot of points if you just forget the plus c, because that's just very integral. Very integral. Okay. Now, let's simplify this further. 1 over 3, multiplying that, x to the cube over 3, and then plus c. Now, simple thing, simple. Just multiply these things. Well, multiply the bottom. What, you thought it was an s? My bad. I guess. Okay. Just multiply the bottoms, because like this on top already good. That's 1. So you don't have to multiply the x's here, since it's gonna turn into x cubed anyways. So x to the 3. Oh, x to the 3 multiplied by 9 plus c. And you got your final answer. Yay! The first integration. Don't worry about it looking like an S. Let me fix that up for future stuff. Okay, that's one example. One example of it. That's still the basic antiderivative, okay? Now, I guess this is the harder part, because this is only like the basic power rule. Okay. So let's go to the basic trigonometry rules. Okay? Recall from your derivatives. Okay, you know, the dx. Yeah, that equals the dx of d over dx of sine. That equals to okay, d over dx of sine. You know that equals to cosine, right? Cosine x. That's simple. So just do the opposite. The integral of cosine x is equal to sine x. Wow! Now recall that for the rest of the the rest of them. Bro, I don't like. That's the part that's hard. Because you know, sine, that's gonna become negative cosine x. The integral of tan x secant x, that equals to, is that again tan x? This is secant x. Yeah, secant x. And then the other one that the cotangent forms, a whole lot of those. cotangent x. It's just these, bro. You have to remember these. These are very integral. I'm gonna keep making that pun because it's very integral. Gonna keep reusing that. It's the same things, okay? Second squared. That is second squared x. That equals to no, it is not my homework. It is not my homework. It is a test that I have to study for. Sadly, but yes. It's truly an integral factor of calculus. But we'll go over the fundamental parts of it. So this is tangent x. And then the other part, you know, cosecant squared x negative equals to cotangent x. Yay! That's all the basic ones! Yay! I haven't even done the tangent x alone. Oh. Exactly. Thank you. The homework answers will not be here. Definitely not. Actually, how do you... This is my issue now. I hate these so much. How about tangent x? What's the anti-derivative of tangent x? Well... How do I explain this? No, it is not through homework. This will not get doxed through homework because I don't have homework to do. It's just me studying. Yes. I'm so productive like that. That's just the basics here. Do I have to go over the arc ones? Arc ones are very, very complex. You know what? Yeah, let's go. First the derivative. So sine first. Arc sine. And now I'm actually just like forgetting something. This I'm fairly certain that it's this, right? I'm fairly certain. I'm starting to forget. Yeah, that's on you. 1 times d over dx. I'm pretty sure that this is correct. This is actually important though, because like this form you will need for trig sub. So yes. Okay, so that. Well, sometimes I don't even know where these come from, honestly. Genuinely, I don't know the background of that. 1 times. So tangent. Since I know it's the... What is it? Since I know that it is sine over cosine, you could technically apply it here. So I think they just basically cancel out. So what you're left with is just 1 over 1 plus x squared. Pretty sure. Yes, I'm pretty sure. I need to double check these. I'll double check them a different time. But I'm very sure. Probably. Not very reassuring, but yes. Those are these. So all you have to do, if you get this form, you just do that. That's the reverse. That's the integral. like dreading this now. D over dx. Second -1. It's arcsecond. That equals to 1 over x square root of 1. Oh yeah, x my. Let me look this up actually now. I'm starting to forget. Arc sine derivative. Arc sine derivative. You know, yeah. Oh, arc second. Okay, I was right in the arc sine. Yes, okay, it is the one I remember. I'm scared. I'm scared. Scared of getting this wrong, but yes. I should be knowing this by now. I passed it. I should know this already. Anyways, it's that. And then the opposite for just put a negative. That's what most of the time the cosine versions, like the ones with C's, they always have a negative after. They're gonna be negative x square root of x squared minus 1. Was it alright. Go do your chores, bro. It's mostly these. These are for the arc versions. Arc versions of those. Okay, our next one. Now that we have those basic stuff. I'm dreading this, man. Let's go to the other integral part of calculus. The fundamental theorem. The fundamental part, yes. If I'm not writing it right. Fundamental theorem. Specifically, the mental part. I would like to emphasize the mental. That's making me go mental. I mean, it's not that difficult of a theorem, honestly, because what it basically is just area 2 minus area 1. Oh, area 1 equals to what's left? Oh wait, no, not area. This is okay. No, wait, this is for the other one. That's not the fundamental theorem. It's supposed to be point 2 minus 0.1 equals to area. Oh. Making it cursive now. Okay. That equals to area. What are those points? Those points are basically just the function parts. So like, let's say f of x minus f of x2 minus f of x1. That equals to the overall thing. Overall area. But it's not a function. It's the integration of that function. Yeah, it's gonna become capital F, not small f. Basically, they're derived from those. Because you know what integrals are? They're basically just the area under the curve. And this is how you find the area under the curve. Yes. So let's say that you have... Oh, wait, no. First is how do you do it? How do you like depict it in math? Well, it's simple actually. You just do this. Snake 0, 1, or like any A, B. Yeah. Snake. Oh no, it should be A at the bottom. A, B. This is your point 1. This is your point 2. It's like point A, point B, you know. This is your starting point, this is your arrival. Point 1 start. Point 2 arrive. Everything in between is just the it's the journey we made along the way. It's just a journey. That's the area in between it. That's what it is. So let's say that you have a function of let's make this simple. I was thinking of a trig, but that's not simple. X to the 4 over 3. Yeah, that's easy enough. Yeah, that's easy. Easy enough. Definitely. Should I make it harder? No, don't leave. Okay. Let's say you have this. And you want to go from point 0 to point 2. Oh yeah, okay, that is a high body temp. Yeah, get well soon, bro. You should, yes, go to the hospital maybe. Okay. It's just... No. Anyways, from 0 to 2, that's your 2 points. So if you want to integrate that, first, we're gonna have to get the antiderivative. Which... First, what to do first, we can take out the constant. I don't know why I wrote those S first, but yes. You can take out the constant, which is 1 over 3. So you're left with x to the 4, right? I'm saying it right as if you could... Yes, you can reply. Reply in chat. But it's that. It turns into 1 over 3. Squiggly line. Points A 0 to x to the 4. I don't know. I just cleaned this up. But now you wanna actually integrate it. Wanna equate it to something. That arrow. So all you have to do is, instead of a squiggly line, let's make it straight. That signifies that you have integrated this thing, this function. So how do we integrate that? You know the formula, the power rule, x to the 5 over 5, because, you know, plus 1 over plus that number plus 1. You get that. But this time, since it's not a it's a fixed interval, you know, you have the point A and point B, you don't need that plus C, because plus C is just any normal like constant that could be added after, because, you know, the derivative, you can do d over dx. It's a constant, you know, it's gonna turn to 0. That's what the C plus C is for. But here you don't have that because it's fixed in an interval. You know you know where it is, you know the area, you know all that stuff. It's real. So all we have to do is just multiply this back inside. So you do that little straight line. You make it a bracket. I prefer a bracket actually, because it's just easier to look at. So now that turns into 15, because, you know, 3 times 5, 15. There you go. This is not the full answer, but you will get partial points if you do get it. But instead, our next task is to just apply this formula, this part. The f of the integral of the function, and then the point B. You minus it by point A. You know why it's B minus A? Well, it's because, you know, point A is quite smaller compared to point B. If you're gonna be subtracting if you're gonna be subtracting A from B, it's gonna be a negative number, which is not the actual area, you know, that's not real. So you have to do it the other way around. That's gonna make you have a positive area. This negative area, that does not exist, bro. How do you get A void. That's not... You're just getting a void. That's why you need an area. So what do we do? What do we do with these numbers? Well, we just have to substitute it. So starting with point B first, you're gonna put 2 to the 5 over 15. No, I need a calculator. I need a calculator. Why did I do this? You subtract that by point A, which is 0 to the 15. Which makes it easier for us, because, you know, this can just slash it out, JoJo it out. It's gone. Gone from the plot after it died. Actually, no. He was still there, but not really. Anyways, yeah, you got 1/2 crosswide. So we're just left with 2 to the 5 over 15. If your prof is lenient, yeah, they'll say this is the final answer. Which, like, yeah, I guess it is the final answer. But let's make it harder for ourselves by multiplying 2 by itself 5 times. That's 5 times. So 2 times 4, that's 4. Multiplied by 2, 8. Multiplied by that, 16. Multiplied by that, 32. So what's your answer? The real answer is 32 over 15. Yay! Yay! 100. Yay. That's our area. That is a small area, but that's only like what? 2 and like 2 over 15 something? Yeah, this is tiny. That also counts. This is just an improper fraction. I just like looking at that to, you know, see what the area is gonna be. That is tiny. Going from all the way from here to here. Yes. It takes how many steps? First you simplify, just permutate. Then you that's the same thing. Then you integrate. Then you substitute. And you subtract it from each other. That's the final answer. Good. Now, it's the meat of potatoes. It's the... Okay, first let's look at this. It's the hard part now. You sub, my favorite. You sub, I sub, we all sub to me. Yes. To me. You sub to me. First of all, what is you sub? You sub is just taking something and then just putting it back. It's mostly taking a part of the function. Part of the function and putting it back. After. And most of the time, that part of the function has a variable. Always has x most of the time. No, it does always have x. It's a function. Always takes ex. So what is u sub? Oh wait, one thing I realized I forgot with all of these is that I didn't have a dx. Yeah, that's gonna subtract points. That's an integral part too. Wait, I forgot about that. It's not squiggly line, it's the squiggly line plus dx. Oh, okay, my bad. I forgot about that integral part. I mean, most of the time you don't notice it unless you're doing these subs. So Yeah, a good learning tool. Okay, first, let's say that you have a funny little problem that's a fraction. You know, let's say it's 3x squared over the square root of 4x cubed. Let's say that dx. Okay, remember the dx. That dx is important now. Let's say you have that. My question now: how do we do this? You know, there's two of these. You can't really do this because it has the square root in it. How do you do it? Well, it's actually simpler with u sub. Because with u sub, you need two things. First, you need the u, then you need the du. What is the du? The du is the derivative of u. And what is u? U is me. No, no. U is just what you want to anything actually. What do you want to substitute? So what's the easiest to take things out of? First, the most complex part of this is just like here. How would you deal with this inner part? You have to look at things in a puzzle piece type of way. Because, say for this, if you get the derivative of 4x cubed, what does that turn into? It turns into like 12x squared, right? And what does that do? It cancels out the squared here in the bottom part. Cancels out that part. That's why we can see the u sub. Most of the time, it's just problem on top. The numerator has one extra above the denominator. That's the most basic things in u sub. But you can apply it to almost anything. You can apply it to even trigonometry. But let's get over that another time after this. So let's say this. You have u, your u is 4x cubed. That's just itself, right? Du, you get the derivative of 4x cubed. And that equals to, like what I said, 12x squared. But remember, the dx. Why do you have to remember that? Because it's a derivative. But, and also I don't know if this is really right, but I like to think of it as if you're deriving as if it's a implicit differentiation type of thing. That's how I think about it. That's why you have a dx. I don't know if that's the actual thing, but might be the actual thing. I don't know. My headcanon. My headcanon is just that everything is an implicit differentiation. But yes. So now, what does that do? Well, now you could substitute things. First of all, you have dx right here, right? You have dx here. You have dx also right here. So how do you put it back into the original? Well, first of all, since now that 4x squared, 4x cubed equals to u, substitute the u. That's it. Simple. Math theory and gamer speak, yes. That's how you do it. Square root of u. Next, how do you substitute the dx? Well, isolate it here. So how do you isolate it? Divide each side by 12x squared. It's that simple. Cross that out. You have dx left. Hey. So what do you do with that information? Well, if that equals this, if that equals that, then that means I can put it back into the formula. I mean, the equation. I can put it back. So that turns into du over 12x squared. Whoa. But you also have 3x squared here. What's gonna happen with those two? Gonna fight? Well, not really. Because the thing is, you can take those out. Because technically, this isn't even real. It's not real. What you can do to like balance things out to make what do you call this? I remember how to do this, but how do I explain it? What they're trying to do is eliminate the bottom denominator. And how do you do that? You use the du over here. Oh wait, no, never mind. I think I got ahead of myself. Yeah, I got ahead of myself. My bad. We don't have to do that. That part. Let's go back. U. 3x squared. This is why I need to study. Okay, I need to review. There, here. I forgot. It's like this. That equals du. Dx. I don't. Did this happen again? I'm starting to forget things, but it's not good. Yes. Yes, okay. This is why I don't like integrals. Let me go back to my derivatives. I know this is the right way, but it's just... okay, wait, no. Go back. I remember now. Eraser tool. Put it all the way. Erase. Gojo. Okay. Yes, the way I did it was right. Divided by 12x. Oh, I need to put ln. 12x squared. Cross that out. Yes. Yes. Okay. This is how it's supposed to be. How would you make this bottom thing turn into this thing? There's 2 ways to do it. No, there's no 2 ways. It's only one day. It's only one way. You do it like this. You multiply it. So what you need to do? Multiply it by 4, right? To make 3x squared into 12x squared, you have to multiply it by 4. But you can't just take out 4 out of nowhere. Or technically, in this case, it's gonna be 1 over 4. But you can't just take out 4 out of nowhere. That's illegal. Not if it's paired with itself. This is 1. This is just 1. That's what it does. You multiply those 2 together, but you isolate that 1 over 4. Well, it turns into just 1. So now they're the same. Right? They're gonna turn into 12x squared. And then 12x squared. But multiplied by 1 over 4. Since those are the same, you can cancel it out. Wait, you can cancel it out? Wait. Not really cancel it out. Right? I think you can move one side. You can remove one side of it. I'm starting to pull things out of the air because I don't remember. I know how to solve it, I just don't remember how to explain it. This is why I need a review, okay? Especially this part. I know this is way simpler to explain, but it's just... Something, take 1/4. Yes. Oh, okay. Yes. Oh, yes, yes. One thing I need to remember is that this is at the denominator. What's the fraction of a denominator that's that positive? Yes, U sub is the first speed bump. I could solve this all in my head, but it's just not in my head. I can solve this all on paper, but like I can't explain it though. It turns into that. The one thing I know. I'm gonna solve this again. Even your brain is confused. Okay. But I know this is this. I think I'm very sure it's right. That I know. That I know. So now that you have those, you can substitute the U back, the original part back. Wait, no, not yet. Wait, no, that's how you... Bro, I'm confused. Well, let me search for a step-by-step. I need help. Let me go back first, wait. You sub step by step. Chat, I'm sorry. I'm confused by myself. Wait, I know why. It's because I did it the other way around. Why did I make this problem? I made it harder for myself. That's why. Scratch that. My bad. Isn't this also a way to use USub? Huh. Wait, no, that wouldn't be USub. I think this would be used with by parts. Don't worry. This is a part of integrals. A part of integrals where you have to learn, you have to repeat. Not in terms of terms, but in terms of problem solvings. If it's not correct, you go again. I'm gonna use an easier problem. Okay, here. The derivative of square root of 3x squared minus 5. Oh, minus 5 dx. This problem. What am I looking at? I just realized, is that cut through? That's fine. We have this problem. So what do we do first? We choose which one could be the U. What can be the U in this problem? Well, I see that this is the hassle. I hate this part. That part is, I don't like to solve that. So that means I can just make it into U. I'll turn it into U. There. And then you get the derivative of that, which is... Oh, wait, not the x, U. The derivative of U is 6x minus... nothing. Because it's a derivative. 6x. Turns into 6x, that's it. dx. Remember that. Okay. Next part, or technically the first part, after this, is you're gonna want to isolate the dx so that you can actually substitute it back. Like that. So now what does that do? Well, let's look at our original. You can substitute the u there, so square root of u, right? So now you also have, you can substitute the du in. So it turns into this. There you go. It's starting to work. It's working out. Right, you have that. Now, what do you see is cancelable in these. You see the x's, these and this. But you can cancel that. So it disappears. If only that could happen. So it turns into this. 1 over u du over 6. What do you do with this 6? And what do you do with this 1? Well, you can take it out of the original problem. Okay, you can isolate it. Isolate the u so that's alone. It's lonely. Are you lonely? Turns into this. It's all coming together. But it's not done. Remember, if you still have u's, that means you have to put it back into the originals. And not only that, but also you can change the problem so that it makes it easier for yourself to actually integrate. Because looking at it like, oh, 1 over square root of u, how do you even integrate that? Well, the easiest thing to do is to make it until it's like numbered exponential form. And how do you do that? Actually, this should have been explained at the start. I'll explain it now. You need to know that if you're gonna multiply to the power of negative, that will always turn into 1 over that number. Okay, it's a reciprocal. That's what it is. And now the second part is that if you have a square root of a number, that always turns into a to the 1/2. Okay, it's the to the power of a fraction. That's what it is. So if you have a to the 3, let's say, it's gonna turn into 1 over a to the 3. Power of 3. Oh, let's write that better. It turns into those. So applying that to here, we can apply both the reciprocal, and also the square root. We can turn that into u into negative 1 over 2 du. Now that's easier. We can actually integrate that. So to integrate that, all you have to do is the +1 and then the over the +1 to the end, +1 and over +1. So that turns into u to the power of 1/2 over 1/2. This should not be a squiggly line anymore. This should be a parenthesis. And not only that, this also should be a +c now, because you've integrated. So with that, what do you have? Well, you can simplify it further. You can put the 6 inside, and then you can take out the 1 over 1/2. The one thing you also need to remember, you should have learned this back in algebra. Is this in algebra? No. Somewhere in like fundamental math, gen math, all those topics. You'll definitely learn this. But 1 over a number over a number that always equals to that number multiplied by the reciprocal of that denominator. C over B. Same thing applies here. How does it apply? To the 1/2. So it turns into u over 2. Oh no, 2u, and then 6, 1/2. Let's see. Remember those. So now that's good. You have those funny numbers. What do you do with those fun numbers? Why is there still a u in here? Well. All you have to do is substitute the original u back in. So substitute this u back into this u. So all you have to do is just 2 multiplied by 3x squared minus 5. 3x squared minus 5 into the power of 1/2 over 6. See, that's it. Genuinely, this is taking up so much time. It's still USAB. I need more to study. This isn't even at the like practice problems part. This is still teaching it. We still have practice problems to go through. You know what? No, I will have that practice problems. You guys won't have to do that. I will have to suffer myself. But okay, how do you simplify this further? Well, you see that there's a 2 and there's a 6. You know what those two are? You know what those two have in common? You can divide it by 2. So you can just turn into a simpler form by turning it into 3x squared minus 5 over to the power of 1/2 times 3. So, dividing 6 by 2, that turns into 3. Plus c. There you go. There you have it. There you have it. You have the integral of this thing. That thing turns into this thing. That is that. Good thing. Good things. Yay. That's still you sub. You sub. I sub. We sub. Okay. All right. Should I make a new page? Let's just edit this to make it larger. That's gonna, oh wait, no, that's gonna kill my RAM. Not really, but yes, it will kill part of the RAM. Let's save some of it for trig sub. I'll do trig sub and then let's make a new one. Okay. Next part is trig sub. Trig sub. Genuinely, this is actually not as bad as I thought, but it depends on the problems. Okay, so what it is just substituting a trigonometric. Okay, I can't write it. I'm not writing that. It's just substituting a trigonometric function into the problem, making things in terms of degrees, and then just putting it back into the original by either arc trig it, or doing a funny right triangle to get the right type of trigonometric function. It's those two outcomes. But the first thing you need to know is the 3 things that each trig function turns into. Or like what to look out for. First thing to look out for is this. If the problem has square root of 1 minus x, this will always turn into this trig function, which is sine x. Like, it's not turning. Okay. A sine x. I should not put 1, I should put A. A sine x. Because you always have to multiply the first number, like the constant multiplied by the Oh wait, I need to remember this. Also, this part. It's always squared. Both the a portion, the constant portion, and the x portion, those two are squared. This always applies to all three of these. But the only difference is just the position of x and whether this is a plus or minus. Second one, I'd say the most easiest one, because if it's a plus, it's tangent. That's what this is. Tangent of x. The last one is square root of x squared minus a squared. 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 Is that? What is that? Well, that is secant. A secant x. It's those three. Remember those three, and you'll be good. Basically it. Oh wait, no, it's not x. Forgot. It's not x that it turns into. It's degrees. I genuinely don't hold the history to this. I just know it's a thing. I think that's why I'm not doing well. It's because I don't fully understand things. It's just that I get given things and I just fully remember it. I mean, I do I'll practice problems, but it's not as in-depth compared to like derivatives. Those are my bread and butter. I love those. You have these. Is equals to x equal to x equal to x. These are the integral functions that you're gonna need. Integral trigonometric functions. Okay. Our first problem to tackle. The first problem to tackle, I checked the flanker, is this. This is pretty simple, right? Pretty simple. What is our A in this? What is our A in this problem? Our A is 2. You know why? Because this thing. But why is it 2 and not 4? Because it has to be A squared. Our A squared is 4. You know, you remember, you're matching this. Matching this. A squared minus x squared. That's the pattern that we found. And what does that equal to? Well, it equals to A sine theta. Equals to x. And our x is just x. You know, that's basic. We know that. So now, what do you do? What does this do for this? What does that do for the original problem? Well, what do you see here? We have an x. You can take that x and just put it inside of the original function here. You can substitute. So it turns into this. Square root of 4 minus, since a is here, that turns into 2 sine theta squared. I know it might seem more complex. It may seem more complex, but yeah, it'll be like that. And the second thing to note, actually, is that we also technically use u sub in this. Wait. Yes, you also do u sub in this. But which part do we u sub in this? Well, it's the x. You sub that part. Because, okay, first, since x equals to sine sine 2x. Yeah. X equals 2 sine theta. Now, what is the derivative of that x? We do need a derivative. Because, you know, dx is still in this problem. Let me erase this, actually. This is part of the problem. Dx is still part of that problem. So we have to substitute it if we're going to be using that trig sub. And how do you do that? Well, it's simple. You just get the derivative of these, which is also pretty simple. 2 sine... Oh, no, it doesn't turn into sine. It turns into cosine. Cosine theta times the derivative of theta. That's the part that we're gonna input into the actual problem. So we're gonna have 2 cosine theta d theta there. That replaced the dx. So now what we're gonna do is just simplify further. We're gonna simplify a whole lot. It's gonna turn into cosine theta d theta. That's the numerator. And the denominator 4 minus, since you have this squared here, it turns into 4 9 squared theta. That's our initial like simplification. We need to simplify further. So second part, just copy the top. You can't really simplify that top part. And then the bottom. What can we do to this bottom part? Well, there's one thing in common. That's 4. So what can you do with the 4? You can take it out first. And you can make the entire problem equal to a very good Pythagorean identity. But not only that, you can also take the 4 out. You can take this 4 outside, since it's also square rootable. So all that turns into is 2 cosine theta d theta. 2. It turns into 2. And then square root of 1 minus sine squared theta. What do you see here? These two, this 2 and this 2, and the numerator and denominator, you can cancel those out. Simple. Simple. So next, what you can do is, first of all, rewrite it so that it's more simple. This just calling 2, yes. This involves a whole lot of simplification. That's the issue with calling 2. Integrals is just simplifying and simplifying further and further. So now, what does this remind you of? Well, if you took calling 1, you should definitely know that it's similar to this little thing. Oh, not sine, cosine equals 1. Should remind you of the Pythagorean theorem. So what is 1 minus sine squared? So all you have to do is just put that on the other side. So cosine squared equals to 1 minus sine squared. You got it. Cosine squared. So there, we can turn that into cosine. You have that. So what's next? You see that there's a square here. There's a square root here. Those cancel out. So now you're just left with cosine theta over d theta cosine. Ooh, Special week. Hmm. Now, what do we do with this information? Oh. I would love it so much that I don't want to take it again. That's how much I love the integrals. What you can do with this is you can cancel it out. It turns into 1. So it's just 1 d theta. But what do you do with that? It's not done yet. Things are not finished. Okay. It's just theta? This turns into d theta. Where do I go from here again? This is why I don't like integrals. Where do you go from here again? I had all this laid out. What do I do again if it's just d theta? Oh, I turned this back. Oh wait, no, never mind. What am I thinking? It just turns into theta. Oh yeah. I forgot. It's just gonna integrate. What am I doing? Oh yeah, it just turns into theta. That's it. Amazing, yes. Why did I think so hard on that? I forgot. But now with theta, what do we do with theta? That's not really a thing we can do. It's not x. That doesn't do anything with the original problem. Well, you can refer back to this. We have x equals to 2 sine x, right? Well, we can also change this. We can change that into x over 2. That equals to sine theta, right? But oh, what do we do? How do we isolate theta? We can make it multiplied by arcsine. Let me write this in another place. We have x, that x over 2 equals to sine theta. If you want to isolate the theta, you can just reverse it by multiplying it by arcsine, which equals to this. Arcsine multiplied by x over 2. That equals to arcsine sine theta. And you know that arcsine and sine just cancels out. That's why you're left with just theta. That's how we have this. This is the answer then. So going back to this, the answer will be arcsine x over 2. Plus c. Plus c. Remember, plus c. It's not done. It's always plus c. Not that also. There you go. Amazing. That's not everything. That's only first part. That's still trig sub. Now it's the amazing part. It's by parts. Integration by parts. Actually, it's not super difficult. It's just that it's a headache if you keep doing it over and over again. Cause this is trig. Not what? Only trig. Integration by parts. By parts. Integration by parts. First things first. It's basically the reverse multiplication rule. Or technically, it is the multiplication rule of integrals, but it's the reverse multiplication rule of derivatives. So, since, right, multiplication rule is like u dv, those look like each other. U dv plus v du, that type of thing, right? Well, for integration, it turns into this. The integral of u and v. The integration of u and v, that equals to uv. Why do those look so similar? Okay. uv genuinely looks the same. uv minus the integral of, I thought it's u dv. u dv minus the integral of u and v. These look the same. There. This is the basic formula for it. And the one part I hate is this section, because it keeps repeating over and over until it's done. So let's get a simple problem from it. Looking on it. Okay. This is a simple problem from it. Let's say x cubed ln x dx integral. Let's say those. This is your initial problem. So now, what are you gonna do? Well, the first thing we have to do is just identify what is u and what is v. First, we have this rule in integration by parts. It's liat, anything, any way you pronounce it. But it's this. It's a logarithmic, and an inverse, and then it's algebra, and then regular trig. So trig, and then exponential, expo. That is a really important rule, because it helps you identify what is u and what is v. First of all, u is udv. Oh yeah. Oh wait, no, yeah, don't flip it. Okay, my bad. This is why I need a review, okay? This is exactly why I'm doing this. There you go. Thank you for the correction. udv equals to uv minus integral of uv. But here, liat. Okay, first, which one here is the most leftmost here? Like that matches one of these parts. Well, ln x matches log, and x cubed matches algebra. So we're gonna use the ln as the first. That's gonna be the u. So what is u? U is Oh wait, someone's calling me. Wait. Okay, back. We have this. U will equal to lnx. Oh. Looks like hx. lnx. Now, our dv that equals to x cubed. So now, what do we do with these? First of all, we're gonna derive the u part. So du that equals to 1 over x, since lnx equals to 1 over x. But dx also. Remember that. And then here, since it's already a derivative, what we have to do is to integrate to get v. How do you integrate v? You do the power rule for integration, which is gonna turn into this plus c. Yes. So now we do this formula, which is uv minus integration of u and v. Right? Yeah. I'm pretty sure this is a derivative. Yeah. This is a derivative. There. Honestly, I don't fully look at that formula because I like doing this. I look at arrow and an arrow and then subtract and squiggly line. That's how I remember things. So first things first is u, which is ln x, multiply that by v, which is x to the 4 over 4. You can put plus c on the outside because it's the same thing. And then you subtract that by the integral of these two, which is x to the 4 over 4. Multiply that by 1 over x. That's only one part of it. Only one part of it. It's not done yet because we still need this side. Next part is to simplify. So all we have to do is just multiply. So it's gonna turn into x over 4 to the 4 times ln x. There's no like actual real way to fully simplify that. It's just that as a given. Plus c, and then minus patience is key. Yes, it is key. X to the 3. That. The reason why it's gonna turn into x to the power of 3 is because this is the same as multiplying it as if it's x to the 4 multiplied by x to the negative 1. And remember that if you're multiplying two exponents together, all you have to do is to plus them. But in this case, since 1 is a negative, all you have to do is subtract them. Put into the 3. There you go, you have this. So now the next part is that we integrate it. Again. How do we make this simpler? Well, we can simplify this further by just taking out the 4 underneath. So this turns into 1 over 4. You put that there. And then you can just leave it as x to the 3. Simple, right? Simple. So our next part is to just integrate the 3x to the 3. Okay, x to the 3, which is pretty simple. That just turns into x4 to the 4. So we rewrite this entire thing again. Yes. Okay, let's not put the plus c yet, because this is gonna have a plus C also. So it's gonna turn into a plus to the 4. And then we put the plus C. You there? Yes. Next is that we're going to rewrite everything again. And then simplify further. How do we simplify this? Multiply the two denominators together. So that is gonna turn into 16. So x to the 4 over 16. Let's see. That C is weird. Let's see. There you go. You have the final answer. I mean, I would say that. But I could also say that I could simplify it further. Yeah, let's go simplify it further. Well, you can multiply everything by 1 over 4. That turns into x to the 4 ln x minus x to the 4 over 4. Let's see. Yay! Now we have the final answer. Yay! Exactly. We need to simplify all the way, or else we're gonna have how many minus points? Minus 20. There. That is integration by parts. Also, there's also another method to do it, which is the tabular method, which honestly is way simpler. I like it a lot. The only issue is it's like if it's repeating, that I don't like. But if it's not, it's a really good tool. I love it so much. Wait, let me give you a little example. So here, let's say that you have That's a good thing to give. Let's say you have x to the ex. I think that might be a little too simple, but yes, sure. Make it a little bit harder. X to the x squared. Yes. So following liat, whatever you say, whatever, yes. The first thing in that is going to be a, which is algebraic, which is x squared. So then you have u, which u equals to x squared, and you have your dv, which equals to e to the x, which is really simple to integrate because it's also e to the x. It's that simple. I love e to the x. E to the x. Now to derive this, oh wait, no, I'm doing integration by parts, but the tabular method. Wrong way. I forgot this is the tabular method. Okay, first you do these things. You put d and you put I, and then you put plus, minus, all the way. I mean, you don't have to go all the way, but yes. So like what I said before, your u is x squared, and your e is e to the x. So you just keep deriving it until it turns into 0. What I love about it, because the deriving part is way simpler compared to the integrating part. But in this case, it's way easier because it's just nothing. There you go, right? It turns into this. But e to the x is just e to the x, e to the x, e to the x. Integral of the x squared dx from 0 to infinity. Let's do that another time first. Trial and error, that's all of math. I'm trying to learn. It's this. So the part that I love about tabular method is that it just turns into a real equation. I mean, a real answer without having to like fully do integration by parts again and again and again. If the other thing is like simple enough, all you have to do is just add an arrow, add another arrow. What do these arrows mean? Well, all it has to do is just It means to multiply those two together. So let's see. So you see that x squared and e to the x have an arrow, right? So all you have to do is just x squared times e to the x. That's it. That's one part. And you see this negative. That's not a negative. That's a subtraction sign. So all you have to do is just minus 2 to the x, and then multiply that by e to the x. Do it for the rest. So this is a plus 2 e to the x. There you go. Why I love this method so much. And you don't remember also the plus c. Don't forget that. Don't forget that. Very important. No, I'm not reading from ChatGPT. I just, well, the problems like that, yes. But this is our answer. This is our answer now. Hey! Okay, let's try integral of e to the x squared dx. Let's try that. Oh wait. I just like it. I mean, you want me to speak very fast? I can speak very faster, but then, like, I'm not gonna do that. I wanna just take it slow. So let's say e to the x squared dx. Okay. I have to remember this again. Solve this. I know this is a simple problem, but like I'm blanking out. Well, I'm just like, gonna instantly think of doing this. Currently this is a college thing. I should be studying, that's why. This is the answer, right? I'm just like fully blanked out on this on my mind. I'm blanking out. I know this is the actual way to do it. It's just that it's the u sub rule, right? See that? Yeah, exactly. That's u. In doubt, that's u. So there. Let me do this fast. du equals to 2x dx, right? So there. Just divide that by 2x, divide that by 2x, cross that out. It's gonna turn into du over 2x. Wait, yeah. Huh. Yeah, oh no, oh no. Oh wait, no, what, wait, no, wait, no. Oh, wait, huh? I forgot, it's 0 to infinity. Honestly, if I were to do this in my mind, which I think is not good, but yes. I know that e to the 0 is just 1. But like, you need to integrate. I'm thinking hard. This shouldn't take that long. You does not work. what did I make? What did I make? This is should not rack my brain as much as it does. Yeah, this is probably why the score in the thing is not great. Is it 0.5? What is this actually? I don't fully know. Please. I don't. I'm still reviewing. Because USub does not fully work on it, right? Yeah, it's gonna turn into a -10. Because you know, I need time to solve it. Answer? Oh, there's an answer. There is an answer to this. I know it is. There is, but like, I don't know if I can solve it. I'm not good enough to solve it, man. For the x squared. Because if you do e to the u, the u can turn to x, and that does not work. How else do you solve that? How else do you solve that? Let's move on first. I mean my final one. My final one is partial fraction decomposition, which is gonna need a whole lot of space. Which part do I erase? I'll erase this part. Oh, that is new. Keeps grabbing. Why not? I can just make us ultra big. Oh no, we are not at that part yet. Oh, that is laggy. Oh, that lagged so hard. Rita, please. Oh. Krita killed my... Oh. Oh. Hello? Hello, is it back? Krita died? Krita, I hate you so much. Why did you just take that much resources, bro? Oh wait, no, makes sense. I just saw that this was like, what, 1 gig? Maybe because I should save something. Nah, I'll just leave it as is. That erasure just like took out how much resources. It killed it for like a bit. Okay, anyways. I'm looking at the clinker for problems. Partial fraction decomp. Decomposition. One thing about partial fraction decomposition is just that it's a very like it's not really technically an integration thing. It's just a fundamental math part of thing. It's to just basically put put the equation into like the most simplest form. It's just another form of simplifying. Or not really simplifying, factoring. Of factoring. Think of it as like breaking parts of yeah, it's very, very useful actually. It's basically just, instead of having like a combined fraction, it's splitting into its tiny components. It's like splitting apart the parts of it. Yeah, I can forget you. No, I still need you sub. It's still important. But yes, I will also need partial fraction decomp. Very important. Let's give this problem. Let's say I'm given x minus 3 over x squared minus x minus 6 dx. And then ln. Not ln. Quickly line integration. So you have those. To do partial fraction decomp in this, first you're gonna break down the actual problem first. You're not even doing the integrating part, you're still breaking things down. How do you break them down? The numerator itself, you don't really have to break down. It's in its simplest form. But the denominator though, you do have to. See this part? What type of equation is this? You see that it's a quadratic, right? You see that's 2x minus 6. Quadratic. Since it's a quadratic, you can use factoring to simplify it further, or just like factor things out more. So let's say 6. What two factors the 6 break down into to turn it into, like to add together to turn into negative x, or like negative 1? That would be negative 3 and 2. Multiplying that together, it's negative 6. Adding that together, it's negative 1. So the actual broken down version would be x minus 3 multiplied by x plus 2. Yes. So now you can put that back into the original. X minus 3 and x plus 2 dx. But this is still one part of it. But now the next part of it is to actually breaking everything down. That's actual parts. Splitting the function even further. So how do we do that? First, you do this: x minus 3. Like disregard the whole integral part. That's gonna come up again, but for now it's still the decomposition part. Should equate that to first how many depending on how many things in the bottom are, like how many parentheses there is. So you take one of them and then you just put it as a denominator here, and you do it with another one, the same with b, x plus 2. This goes on and on and on. The more like parenthesis functions here in the bottom there are, it'll go on like almost infinitely, honestly. Just depends on how large of a fraction you have, how complex it is. But yeah, breaking those down. Now what you want to do is just to get a and b, because a and b is just the two numerators that you don't have. Those are unknowns. And that's unknown. B is unknown. So what you want to do is just first multiply this side to cancel it out. Multiply this side by itself like the denominator by itself. But here. So how do you do that? It's like x minus 3 minus 3 plus 2. Do that for the rest here. I don't want to write it down because it's a bit cramped. So you're gonna be left with x minus 3 equals 2. What's missing in? This would cancel out here. So you don't include that. All you have is x plus 2. A plus 2. You're adding that in here. What can you cover? X plus 2 and x plus 2 is a common thing, so that you don't have to put that. So now you're left with x minus 3. So that's going to become b x minus 3. There. So now that you have that, what can you do? First you multiply, substitute. You need to isolate one part. Well, one part on the right. So you can make either a 0, like you can make this part 0, you can make this part 0. Either way, you can solve for the rest in the end anyways. But how do you make, okay, let's say a. How do you make a 0? First, you just substitute x with negative 2. So let's say if x is equal to negative 2, it's going to turn into 5, negative 2, 5 negative 2 minus 3 equals to, since negative 2 plus 2 equals to 0, you can just make that entire part 0. And now you're left with b. b negative 2 minus 3. So now simplify that. Negative 10 minus 3, negative 13. And then b negative 5. This is a fraction. Negative 13 equals to b, negative 5b. 13 over 5. Yes, that's still integratable, but like, that's such a... Oh wait, I need to fix that up. It is integratable, but like, it just looks so off. I don't like it. It's not as clean as, you know, making things whole numbers. So now you can cancel out the negative b on one side, or the b on one side. Not the b, I guess the 5. The negative 5. You cancel out the negative 5 on one side. And negatives here also cancel out. So you're left with 13 over 5 equals to b. You have your b. Now we can do the same for a. But now for a, what can you do to make b 0? You can substitute x with 3. Let's write that again. 5x minus 3 equals to a, is that x plus 2, x plus 2 plus b x minus 3. Right? Yes. So now substitute x with 3. So then that's gonna turn into 3 minus 3 equals to a3 plus 2 plus 0. So now you can simplify more. 15 minus 3, that's 12. 12 equals to a times 5, a5. Divide both sides by 5. Cancel out that 5. A equals 12 over 5. Once again, I don't like it. It's not a whole number. But that's just my preference. There. So B is 13 over 5, A is 12 over 5. So what do we do with that information? Well, now we have the actual problem now. We have the simplified version of the actual equation. So 5x minus 3, that equals to x minus 3. Oh. Minus 3, x plus 2 equals to, first A, 12 over 5 x minus, and then 12 over 5, wait. 12 over 5 over x plus 3. No, x minus 3, I mean. Plus that with 13 over 5 x plus 2. And then you can simplify that further by just putting the weird fractions in the top and putting them in the bottom. Like flip, or getting the reciprocal, and then that's it. Minus 3 plus 5 over 13 x plus 2. There you have it. This is still one part. This is still one part of your actual integration. It's not even integration yet. That's still cleaning things up. But at least it's cleaner. Now you get to the actual integration part. And to do the actual integration part, you just have to let me drink water. Actual integration part is, can we simplify this further? Let's do it after. Actual integration part is this. You just add the dx's and the integration back. But this time, you can distribute it to both of those so that they add up. X plus 2. There you go. Dx. Now we can simplify it way further, which is just putting things on the outside. So 5 over 12 can be on the outside. You can have 1 over x minus 3 here. The same with the other side. 5 over 13 on the outside. 1 over x plus 2 here. Dx. Okay, next, let's focus on this one. Let's focus on the left. So to integrate this, all you have to do is u sub. How do you u sub this? U sub this using this part in the bottom. So that will turn into 1 over u. Since u is equals to x minus 3, du will equal to 1 dx. Since that's 1 dx, which divided by 1, it's the exact same thing. It'll turn into du. That's 1 over u. Oh, I didn't actually. I didn't show this. I forgot to show this, but you need to know at least that du over u is equals to lnx. Yes. Or like at least dx over x, that equals to lnx. Yes, it's 5. That's 9 p.m. already. Okay, wait, let me finish this and then it's time to go soon. So after that, 5 over 12 put it back. X minus 3. Oh, ln. That integrate. Integrate that. 5 over 12. And u. So it turns into ln x minus 3. You can do the same with the other side. And then the other side, basically it looks like the exact same thing. So it turns into 5 over 13 ln x plus 2. Yeah, I should have moved the plus c in the outside, but basically it. 5 over 12 ln x minus 3 plus 5 over 13 ln x plus 2 plus c. That's your final answer. That is the actual integration part, okay? This side was just the this side was initial setup. Oh. Initial. And this side is the end, is the actual integration. Yes. Okay, that's still the initial, and then the integration part. That's what this is. A whole lot of those. That's why partial fraction decomp is really important. Let's see our work. This is nothing, bro. I'm so cooked for the test. No, I really do want to. No, I will pass. I can do it. Okay. I think that actually is good for today. That honestly, I'm surprised. We actually that was a lot longer than I thought. All of those okay. What did we tackle first? We tackled yes, good for the calling too. We tackled antiderivative, then we tackled the fundamental theorem, then we tackled u sub, then we tackled trig sub, then we tackled by parts. Then I got stuck on that e to the x squared. Genuinely, I'm forgetting. I don't remember how to solve that. I should know, because I'm pretty sure it showed up on the test already. I'm pretty sure I got it wrong. And then afterwards, partial fraction decomp. Okay. So how did you guys enjoy that? Please get easier after calling 2. All I know is that rigid bodies is gonna kill me. Please don't. I want to have an easier time, maybe. Please. How did you guys enjoy that? Good stream. Good stream. Genuinely, that is actually honestly a lot. I liked it, honestly. I remember before I used to teach some of my friends just how to like. I realized some of my I used to teach some of my friends before on like physics and also some calculus before, you know, in derivatives. I used to teach some of my friends there. I guess that's also some part where I learned these a lot. I think that's also why I learned I was really good at derivatives. It's because I taught it to my friends. Integrals though, I am dying. I guess this is also helping because, you know, at least I helping others teach or helping to teach others. That is just makes me understand things a lot more. And you know, actually the corrections also really helped me a whole lot. And you know, and this just reminded me that I really have to study more. The e to the x squared, I'm dying. I'm dying. But yeah, I hope you guys enjoyed. It's already like 9:05. I think it's good to call it a night. So thank you chat for staying. You know, it's been a good stream, but a lot of math. Anyways, see you guys. Good night.